So, yeah, next up we have Edward. Edward got his PhD in medical imaging from the University of Auckland. He's currently a research fellow at the Auckland Bioengineering Institute and a lecturer at Telkom University, Indonesia. Previously, he was a Scrum Master and a software engineer in various industries, including NLP, radiology information system, motion capture and tracking for Avatar: The Way of Water, and computer vision. So, Edward, take the stage. You never had it.
Yeah. Okay, that's fine. Yeah, I know. Sorry, borrowing some colleagues' stuff. All right. Yeah. Hi, everyone. My name is Edward. I'm a research fellow at the ABI. Thank you for the introduction. Today, I'm gonna talk about a project that we did called DIFF. It's not a typo. It's we actually read it DIFF, a latent diffusion model for 3D echo synthesis. So a little bit of a background. Basically, from the first talk yesterday from Debbie, we know that echo is the most widely used modality for cardiac assessment. And basically, deep learning models are actively developed. And as we know, are very data hungry. And because of this, in medical imaging, we need a lot of images and labeled data. However, it is the cost to acquire these images are rather costly, time-consuming analysis, have to be performed by cardiologists and so on. And also, this data are mostly not publicly available because of patient privacy. So in terms of 3D echo, it is more challenging to analyze. You can see the image here. The quality is not so great. You can practically delineate the left ventricle here, but most of the time you will have some error. And this is because of the limited spatial resolution, poor contrast to noise ratio, and complex noise characteristics, right? And because of this, we need a lot of data to train a deep learning model to actually produce, let's say, a segmentation in a more reliable manner. However, it's not available, so we probably can use of synthetic data. Right, so jumping off a little bit from medical imaging to another field. So for synthetic data, it's pretty much have been used in other fields such as computer vision. On top right here, you can see an image of a road. This is from the German sign benchmark dataset, where basically a neural network is tasked to recognize a sign on the road. And as you can see here, synthetic data can provide alternative for training data, where you can basically add just like a flying sign here, or on the train over there, the train sign over there, where then you can train neural networks to actually see signs on the road. So as you can see, this is not realistic at all, but it's a possible thing, at least for neural networks, right? So it can be utilized to improve downstream tasks such as segmentation. On the bottom right here, you can see an image basically from video games where you can generate this image in an easier way. So you can have segmentation labels and you can have the image rendered in high quality. So this synthetic image is basically almost free to generate, whether it's manual or automatic, and possibly comes with free label. So, and the best quote from yesterday is, why not throw it at a neural network? Right, so neural networks seems to be able to solve a lot of things like this. So actually, this is not a new problem. We've seen synthetic data generation through GANs in the past 6-7 years. And the original DAL-E also was based on GANs. So now this DAL-E 2, I think from 2021, is based on diffusion model. It can generate images from text. It can also have the capability to have the image generated based on another image or image guidance. Right, so we can actually more flexibly create our data. And this is based on a new approach called the diffusion models. So what is diffusion model? So a little bit of that is basically comes from thermodynamics equilibrium, which I'm not an expert at, so please don't ask questions on that field. So the idea is very simple. There's two process, which is the forward diffusion process. The idea is you have data where you add some small amount of noise sequentially, and then in the end, you basically destroy the data into pure noise. And there's also the reverse diffusion process where you try to recover this image back to its original state from pure noise to the original image. And what does the neural network does here is basically to learn to identify this small amount of noise from a pair of image. So in practicality, in terms of training, what it does is you throw a bunch of pair image within with a pair time steps, where it learns to identify what noise it has to remove to recover this image to the previous time step. So it's very simple like that. Okay, so in the end, what it does during inference, so it can go from pure noise, and then you feed this to the diffusion model, and it will try to clean up the noise for a huge amount of time step, and in the end produce an image depending on what the data you were training with. So that's basically the diffusion model in a very simple way. So in terms of experiments, before we jump back to echocardiography, so we started with very simple experiments. So we started with this Oxford flower data set, which is available for computer vision. And we started with a huge amount of data, around 8,000 images. We tried this to train the diffusion model, and we can basically generate this kind of synthetic data, which is basically have a lot of variation and also high quality. And we tried to reduce the image to only 800 to test the capability of the diffusion model, right? Because in medical imaging, we don't really have much data. So we reduced this to 10% of the data. What we can see is the diffusion model is still capable to produce a lot of variation of the image, but you can see the quality of the image, or like the color intensity, is actually quite decreased. From there, we also test this on a Pokemon dataset, just to see, okay, if the diffusion model can actually generate this kind of high quality and diverse image, can it actually generate Pokemon? So yeah, the answer is yeah, we can. But the problem is, you kind of see it's a Pokemon. You don't really see where the eyes are. You don't really see where the legs are. So it kind of understands what are the features of Pokemon, but it doesn't have this capability to discern what semantics are there. So most of this is basically caused because the Pokemon dataset that we use is basically don't have point correspondence or like similarities in terms of the location of the eyes and so on. So we kind of get the idea of what the capability of the diffusion model able to do without any guidance. So this is totally random. So now we jump back to medical imaging a little bit, where we try actually to generate synthetic image on 2D echo images, which is from the Camus dataset. So again, we choose like a low amount of numbers, 200 images from 100 cases, basically from AD and ES. So it is able to do this, to generate synthetic data for 2D echo images. And then from there, we now are pretty sure that we can also do this for 3D echo. So we start to do this on 3D echo. So the result wasn't so great. So this is not an actual result. This is just an illustration. But when we apply it to 3D echo images, it starts to fail because the high dimensionality of the image, and also like its high computation cost, and it cannot really learn the attention mechanism correctly on 3D images. So we thought, okay, this is not a really good approach to do this. And then here comes another approach, which is very much used nowadays, which is the latent diffusion model, or more famously called stable diffusion right now. So it's a two-stage approach where we have VAE, or variational autoencoder, that learns the image representation. So it learns to compress the image into the latent space distribution, where it actually then decoded back into an image. And this latent code from the latent space representation, we can use it to sample for new images. And what we are training the diffusion model is on the latent representation. So not on the pixel level anymore, but on the latent code. Right. So in essence, then this is actually reducing the computation capability, the computation cost, and also much more faster, because you have to run the inference or for diffusion model in several time steps. So this is what we are going with, the LDM, latent diffusion model. And for training data set, we are using MITEA dataset. This is the one that Debbie showed yesterday. We collected a large amount of 3D echo images that is labeled aligned with MRI data. So we have high quality label based on CMR registered data. We have in total 536 images at the time this method was developed. And basically DIFF-E is a wordplay from DAL-E, a latent diffusion model for synthesizing realistic 3D echo with high quality label. So not only the image, we want to also generate the label, because even if we can generate a massive amount of image, it is probably hard to also provide the ground truth segmentation. So what we want to do is not only provide the image, but also the labels. And again, it's a two-stage framework. We choose a KL-VAE, correlator VAE instead of VQ. And we use the diffusion model for the second stage. And yeah, from the media data set, we split this actually very similar to the way the original media paper was done. We used 428 cases for training and 108 for testing. And the input is reshaped and padded into a certain shape to make it the same. So it's 160 by 161 by 128. And we basically just concat the image and the channel on the fourth dimension, basically. Okay, so let's go to the first stage now. So the first stage is basically just a normal KL-VAE, where you have this image on the left. It's image and channel on a separate dimension there. And you just pass it on to the VAE. It learns this latent representation, which you can see over there. And it reconstructed back into the image and label. Optimization is pretty straightforward. It's L1 for the image, cross entropy for the label, and then you regularize this on the latent space. The problem with VAE is it's notoriously known to have blurry images, so we have to add an extra term to optimize the quality of the image. And here we opt for perceptual loss, where you actually have to deconstruct this into a grid of 2D slices. So we do this for each axis. So we built this 2D slice, 2D grid for each of the slices, and we push this to a 2D LBIPs, which is a standard for network to recognize perception. And this is based on pre-trained VGG. So unfortunately, we have to do this in 2D because, as far as I know, there's 3D LBIPs or perceptual loss for 3D is not there yet. So I think it's a great subject for thesis if anyone wants to do that. But anyway, we optimize this in a 2D way. So there will be a slight disadvantage of using this method. So the question now, does it actually help? So this is an example of VAE reconstruction. So without talking about the diffusion, this is just a test of how good is the reconstruction of the VAE. So on the left side, you can see the ground truth, and this is without perceptual loss in the middle. And on the far right, you see it with perceptual loss. So we pretty much recover the characteristics of the 3D echo. Of course, this is just one slice of this, but you can still see also there's this very light delineation or watermark of the left ventricle. So it's not really perfect. So there's this, yeah, so there's this line you can see maybe over there. So if we actually have to measure the reconstruction capability in terms of SSIM, while this is actually looks almost perfect, if you see it by eye, in terms of SSIM, it's only around 84%. And for the VAE itself, the hyperparameters or the setup is basically we have just using like a UNet-like or encoder-decoder architecture is it's 8 time down sampled, which is like three layer down. And we train this for 200 epoch with, it takes around 15 hours or 5 minutes per epoch in an NVIDIA 800. Okay, so the next part is actually the diffusion model itself. So the diffusion model is basically a standard model nowadays that you can basically use directly from the internet. However, most available models are for 2D, so we had to adapt this for 3D. And we use the conditional diffusion model, which means you don't condition it based on text or image or any other things. A lot of different training parameters here, but yeah, but the idea is basically now you have this latent code, which is much smaller, which is around 20 by 20 by 16, which can be sampled from this latent code. Because of this smaller dimension, it allows also to use a large batch size, which speed up the training. Nothing special with the optimization. The loss function is basically just L1, and you train it for 50,000 iterations and takes around 12 hours. Okay. So in essence, once you actually train these two networks, you can start generating data. So the data generation process works again in two stages. The first stage, basically, you generate plausible latent vectors Z from the random noise, which is colored on the step 1 over there. So you have this small voxels on the latent code, and then you generate the plausible shape, plausible latent code set on there. And then the second stage is basically you throw away the encoder part of the VAE and you only use the decoder, and then you basically decode this plausible latent code, and then you get the random synthetic data. So in total, the generation step itself only takes less than 1 second per case, which is really fast. So you can generate a lot of data by just using the diffusion model like this. Okay, some qualitative results here. You can see the real image looks like that, and then the DIFF image looks slightly blurrier. I don't know if you can actually tell, but there's still some checkerboard patterns over there. But so far, the quality is actually like really good compared to a previous method that is from a year ago. This is Hagan, where it also tried to generate 3D echo images. And we trained this using the same data, same split and everything, and then just using the original setup. And you can see the image quality is not up to par with the real data, and also you can see some duplicate data because GAN is known to have mode collapse. But the best part of DIFF is actually comes with the label itself. So not only generating the free synthetic data, it comes also with already the segmentation of the left ventricle. Okay, so now that we know how to do that, we basically generated 5,000 paired 3D echo images and label. This is basically if we project the data distribution into 2D space. So we have the DIFF on the left side only generated 428 synthetic cases, the same amount with the training data. We can see the distribution is pretty much within the range, and we generated basically more 2,000 to 5,000, where we basically cover the whole latent space distribution over there. Okay, the next part is how can we actually check, or how can actually evaluate if our data is actually good. So this is a synthetic data evaluation pipeline from the Van der Schaar lab. Basically, what happens when you generate synthetic data, here you have to evaluate the data. But then how do you evaluate the data is basically based on some metrics that we'll discuss later. And this evaluation is basically a way to actually evaluate the realism of the data. But in our case, we also want to use data for something else, for downstream tasks such as segmentation, and this is where the utility comes to play. So there's two things that we have to evaluate here. And this is another really good tool from I think Singh et al. Yeah, Singh et al. It has a code and GitHub repo that actually will measure this criteria for you once you have your synthetic data and real data distribution. So basically what it says is this is based on the experience with 100,000 chest X-ray images, where you can measure this based on 4 criteria in terms of fidelity, variety, privacy, and utility. And the right image here is an interesting experiment where it is shown that diffusion model marked with purple has higher variety and privacy level than the GAN counterpart, whereas GAN have higher fidelity. It is well known that GAN has a higher fidelity, but also less diversity because of the mode collapse. Okay. Another conclusion that the author made is synthetic images don't have to be perfect. And so this is basically an example of mode collapse synthetic image that can also contribute to accurate classification. It's very interesting. While GAN result in mode collapse, where the image are probably redundant or duplicate, it can still contribute to improve the, let's say, segmentation accuracy. And they provided also a graph like this, where actually low variation here doesn't necessarily means it's contribute negatively to the accuracy. Here, actually, the contribution of the accuracy is actually higher. Right. So this is a very a good conclusion of in terms of comparing between realism and utility. So in terms of medical imaging, I think it's important to have a better utility than realism compared to, let's say, computer vision or images in the wild, where you actually care more about just the fidelity. Okay, let's go back to our results. So in terms of our result, we have to evaluate this based on this realism metric, basically. So we calculate the Frechet inception distance, basically the distance between the real versus synthetic features, calculated using the inception network. So when we compare the real or the test data compared to the training, the FID is 14, and in terms of DIFF is pretty close as well as 13.7. Compared to the GAN counterpart, the HeyGAN, we tried 2 different variants, and it has a higher FID. So this confirms our result that the E result in terms of synthetic data distribution is feature distribution is much closer. Also, we calculate the improved precision and recall, and we basically also have higher score compared to the GAN, and we can see this GAN one collapsed to 200. The GAN 256 actually the IPNR is almost 0, basically because of the mode collapse. And finally, we also check for diversity on the data set. So in terms of diversity in the data set, it's a difficult problem to measure. So we use MSSSIM, multiscale structural similarity. Basically, we did this by comparing a pair of data within its own data set. And so we can see the E actually excels in terms of the MSSSIM, but this is also because of in the training data itself, it has a scan rescan. So that is basically expected, but we have a pretty much diverse data set generated by DIFF-E. And finally, it's not complete without actually testing the utility on the DIFF-E itself. So we retrained on the segmentation network, but on this time we actually do it a bit aggressively. So instead of adding only a little bit and cherry picking the data from the distribution, we actually add just 2,000 data directly. So we only have the real 400 data plus 2,000 static data. And we see only a slight performance, luckily. So yeah, so that's great, which means the neural network, even though the data is imbalanced, you can actually see probably the features that is in the synthetic data generated by DIFF-E is pretty much similar. So we still see a slight drop, but we probably can improve that. Okay, so yeah, so what we learned so far. Actually, the feature similarity matters. So we saw in the VAE reconstruction before, the SSIM is around 84%. I think if we manage to increase this, then probably it will be better because then we have similar features. And yeah, balancing through synthetic data matters. We have to basically cherry pick the data and then measure the distance between the features and so on, actually, and then make sure that the data actually acts as augmentation and complementary on the diversity. So again, the realism is not the main goal, utility is, but because of that as well, the different augmentation types, such as like shearing and really very weird rotation or whatever, a non-plausible shape and transformation can also be used. Okay, so that's all basically from for DIFF-E. So what's next? So next step from DIFF-E, basically, we would like a way to actually verify the utility early. So without going through all this process, we want to verify the utility early because it's the main goal. And while it's counterintuitive, improve realism in this case, because we know, I think we are certain now that this SSIM actually contributes quite a lot into the feature space. One of the way to do this is switching to VQ-VAE architecture and also incorporate GAN in the VAE itself. And we would like to do more on the conditional LDM, so we can constrain this or we can guide the image generation using different different modalities or different input like sketch, labels, PCA, and text. Okay. Yeah, the takeaway message basically DIFF provide effective and efficient means of generating paired 3D echo and label, and improvement image quality may improve downstream tasks such as segmentation. And DIFF is actually a generic framework for synthetic data generation. You can basically download the code on my GitHub. It's open source. And if you have an image and a paired label, you pretty much have to just configure the image shape and the labels itself. So it's pretty much ready to go. If you would like to replicate the result of DIFF, the dataset is also available. You have to send a request where it has to be approved. But yeah, that's all from me. One more slide, if I may. This is a self-advertisement actually for the ABI members. So if you are at ABI, whether a student, a postdoc, or staff, and you want to learn more about machine learning, I'm planning to gather like a group to discuss the state-of-the-art machine learning techniques and plan a workshop or talk or something like on diffusion, LLM, neural implicit representation, and so on. You can sign up here if you're interested. There's a Google form there. You can also use the QR code. Okay. Yeah. Thank you.
Are there any questions?
I have a good question. Great talk, Edward. Nice to see you advance on this topic. When you are generating the images, are you using the Cartesian coordinates or are you using the polar space where the scan lines actually?
Yeah, we are using the Cartesian coordinates. Yeah, so it depends on what we want. Yeah, if we have the radial or the polar coordinates, we can also do that.
Yeah, because an advantage if you use that, it's you have a lot of features because of the interpolation of ultrasound.
Correct.
So if you go to the space, you have less complexity.
Yeah,
and probably the noise also will look more trivial.
Yes.
And the other aspect is, I don't know how much access you have to the parameters of the scanner, but there are other confounders that can be removed regarding intensity, contrast, state.
Yeah. Yeah.
So probably if you remove all of those, your space of learning is
correct. Yes, thank you. So the main difficulty on this is actually like to actually generate or replicate the spectral noise characteristic correctly. But also, if the advantage of using this is basically then we can also have this segmentation that goes out of the cone. Yeah. While you have to handle that separately on the radial for.
You can convert it to other space. You just apply the same transform.
Yeah. But yeah, thank you for the suggestion.
Can I ask Gonzalo a question? So one of the reasons we haven't done that is because the field of view is sometimes not adequate to cover the left ventricle. So if the left ventricle is outside the cone, in Cartesian coordinates, we can still capture that. But if we, I don't know, if we make it.
But you are guessing. You have it, but it's not true, probably. You have it from the MRI, but it's not, the information is not there, so you kind of are cheating anyway.
But I think if you use that in a Cartesian coordinate system, it can kind of use the, I guess, the contextual information to come up with some, like at least a guesstimate, which is based on something, not exactly nothing.
Why is the information not there? I mean, the image information is not there, but you get shape information from what is in the field of view.
Yeah, but you can have multiple different configurations that probably they will give you all the same ultrasound image. So in the segmentation out of the image, probably you will have the same result. If you have it or not.
You can probably hallucinate the labels in the end if you want.
Yeah,
and if you want
to do another step just to
add
back again.
But that was the reason why we did it on the Cartesian space.
So you showed that sort of T-SNE style plot where you showed the features in 2 dimensions. And so, some of them are sort of, they're all sort of in the same space as the data that you train on, of course. Have you looked at whether the ones that are more like outliers, or if somebody else did that, whether that's more valuable to the training or the ones, or the diversity within this?
Yeah, good question. Yeah, we actually haven't looked of the images like. Maybe we haven't really cherry picked the images. We just like throw them at once. But yeah, that we would like to look at those, especially the one on the outliers. And we would like to see on the shape on the generated image what it looks like. Yeah.
Other people, like when they cherry pick, do they prefer to cherry pick the outliers, or do they prefer to cherry pick the ones closest?
Yeah, in terms of like the distance between the data sets, also we have to probably figure out how big the distance that is like optimal about that, and then we check if it's like this if it's very similar or not, and we have to measure that. But I think most people are taking within the interpolation space.
Any other questions online?
This is zero D model.
Thanks for the opportunity. Yeah.
Thank you.
Give another round of applause.